In this video, we're going to have a look at two-step change probabilities and the difference between replacement and non-replacement after the first event. So two-step change probabilities involve calculations that have two events. So for example, rolling a dice twice or flipping a coin twice. Sometimes the second event is repeating the first event. So drawing out of a bag of marbles. On the second event, drawing out of the same bag of marbles. Now the probability is going to be different if our first marble we draw out is replaced in the bag before we draw out our second marble. So using a tree diagram, we're going to have a look at how replacing or non-replacing after the first event will impact on our probability calculations. So the first example we're going to have a look at is where it is replaced after the first event. So a bag contains 3 red and 2 blue counters. A counter is taken at random from the bag, the colour is noted, then it is returned to the bag and the second counter is chosen. We know that it is replaced because it tells us in the question that it is returned to the bag before the second one is chosen. So we want to go ahead and show the possible outcomes on a tree diagram. So when I draw out my first counter, I'm either going to draw out a red or a blue. Then on my second draw, again, I'm going to have 2 possibilities, a red and a blue, a red and a blue. So I have 4 possible outcomes. I have a red and a red and a blue and a red, and a blue and a blue. So now I want to go ahead and assign the probability of each of those outcomes occurring. So to do that, I need to go ahead and assign the probability of each step in my tree diagram. So on my first spin, the probability of getting a red is 3 out of 5, and on my probability of getting a blue is 2 out of 5. Now because when it goes back into the bag after I draw it out, the probability is going to be the same on my second draw. So the probability of getting a red is 3 out of 5, and the probability of getting a blue is 2 out of 5. So now that I've gone ahead and assigned those individual probability for each step on my tree diagram, I can work out the probability of my final outcomes. I do that by multiplying each step along the way. So the probability of getting 2 reds is 3 over 5 times 3 over 5. So multiplying my numerator and denominators together, it's going to get me 9 out of 25. The probability of getting a red and a blue, so the probability of getting a red is 3 out of 5 times the probability of a blue, 2 out of 5, so that's going to equal 6 out of 25. Probability of a blue and a red, so that's 2 over 5 times 3 over 5, so equals 6 over 25. And the probability of getting a blue and a blue, so 2 over 5 times 2 over 5 equals 4 over 25. So the probability of each of my outcomes have been worked out. Now if I add all of my probabilities together, so 9 over 25 plus 6 over 25 plus 6 over 25 plus 4 over 25 is going to give me 25 over 25 or equal to 1. So that is the probability of each outcome when I am replacing the counter after I draw the first one out before I drew the second one. Let's have a look at an example where I don't replace the counter. So we've got the same question, but this time the second counter is chosen out of the containers remaining in the bag. So for my second event, I'm drawing out of the 4 containers that are remaining. So my tree diagram is going to look the same as my tree diagram from the previous example. I'm going to have a red and a blue, a red and a blue, a red and a blue. Now that I've done my tree diagram, I can go through and list my possible outcomes. And you'll notice that there hasn't been any change yet. My next step is to go ahead and assign each of those steps on the tree diagram a probability of occurring. So on my first draw, the probability of getting a red is going to be 3 out of 5, and the probability of getting a blue is going to be 2 out of 5. Now this is where it changes if I don't replace the original counter. When I do the probability of my second event, this time it's not going to be out of 5 because there's only going to be 4 counters left. So my probability is going to be out of 4. So the probability of getting a red on my second draw, if I got a red on my first, is going to be 2 out of 4 because I'm going to have 2 red runs remaining out of a total of 4. And the probability of getting a blue is going to be 2 over 4. Now the probability of getting a red, if my first counter was a blue, this time I'm going to have 3 red runs remaining. So it's going to be 3 out of 4. And I'm only going to have 1 blue counter remaining if my first draw is a blue. So that's going to be 1 over 4. So you'll see that the probability of my second draw changes if I don't replace the counter after the first draw. So now I can go ahead and calculate the probability for each of those outcomes. So the probability of getting 2 reds, 3 over 5 times 2 over 4, which equals 6 over 20. Probability of getting a red then a blue is going to be 3 over 5 times 2 over 4, so 6 over 20. Probability of getting a blue and a red, 2 over 5 times 3 over 4, which equals 6 over 20. And the probability of getting 2 blues is going to be 2 over 5 times 1 over 4, which is going to be 2 out of 20. Now, each of those probabilities can be simplified. So 3 over 10, 3 over 10, 3 over 10, and 1 over 10. Now, if I add all of those probabilities up, like I did in the previous example, so 3 over 10 plus 3 over 10 plus 3 over 10 plus 1 over 10, still gets me 10 over 10, which is equal to 1. So the total probability still equals 1, but the probability of each outcome is different.